In this video, we'll be treating everything related to heat and temperature as relevant to your JAMB exam. So take a look at these questions from 1 to 20. If you find any question that is unfamiliar to you or you can't solve, then stick around till the end of this video because you have so much to learn. But if you can solve every single question here or majority of the questions here, then you already have a solid foundation on this topic and you don't really need to watch this video. Alright, without further ado, let's get into it. So we're going to be using a blank page to solve the questions, and we're going to be following them through from number 1 to 20. That means if the question you're unfamiliar with is like maybe number 16 or number 18, then you have to skip towards the end of this video so you can get the solution. Alright, so we'll be starting with number 1. This is from the topic linear expansivity. I'm just going to give a brief recap on linear, area, and volume expansivity. Take note, volume expansivity is also called cubic expansivity. And the reason I'm treating them together, or somewhat a summary together, is because they have similar formulas which you need to know. It's only volume expansivity that has some extra formulas, but generally the formulas are the same. So linear expansivity is represented with the symbol alpha. Area expansivity is represented with the symbol beta. Volume expansivity is represented with the symbol gamma. I think I should just use. So linear expansivity, area expansivity, volume expansivity, and they have similar formulas. What do I mean by that? So for area expansivity, area expansivity is the change in length. We use delta to show change in length per unit length per degree rise in temperature. In expanded form, that's going to be like this. Change in length is L2 minus L1. That is final length minus initial length, all over initial length, which is unit length, and degree rise in temperature, which is theta 2 minus theta 1. Okay, so for linear expansivity, we have change in area per unit area per degree rise in temperature. And you can guess what we have here as well from this, area 2 minus area 1 all over. Then for volume expansivity, we have gamma is equals to change in volume all over unit volume times what? Change in temperature. Now the relationship between alpha, beta, and gamma is as follows. Beta is equals to 2 times linear expansivity, and gamma is equals to 3 times linear expansivity. Alright, so with this we should be able to solve that question. Question says a bridge made of steel 600 meters long. This is the initial length with a daily variation in its length if night and daytime temperature are 10 degree and 35 degree respectively. So these are the change in temperature. So 35 minus 10 will give us the change. The linear expansivity of steel is, so we're given the linear expansivity, we're asked what is the change in length. So we're looking for change in length. If we use our formula of linear expansivity, you find out that linear expansivity we're given, which is 0.0000012, right, per Kelvin, is equals to change in length, which we are looking for, all over unit length, which is 600 meters, they give us in the question, times what? Change in temperature. Remember, our temperature change is what? 35 minus 10, which is 25, right? So times 25. All I have to do is cross multiply, and so we have area expansivity is equals to, so convert this to standard form. If you convert this to standard form, just a shortcut just to count number of zeros. Actually, just count number of zeros: 1 2 3 4 5. So we have 1.2 times 10 raised to the power minus 5 times 600 times 25. Now another shortcut is to count the number of decimal places. So 1 2 3 4 5, and then we get 1.2 times 10 raised to the power minus 5. Remember, when you are counting towards the right, you have to use negative, but when you are counting towards the left, you have to use positive. Just remember that. Okay, so let's simplify. Can we simplify this without a calculator? To an extent, yes we can. To an extent, yes we can. Or, so we don't waste time, we can just press 1.2 times 600 times 25. So 1.2 times 600 times 25 on your JAMB calculator, you have 18,000, right? 18,000 times 10 raised to the power minus 5. To simplify this, we are going to get our answer in what? In meters, right? But if you look at the options, our options are in cm. So to convert meters to cm, what do? We multiply by 100, because 100 cm is equals to 1 meter. Therefore, whatever we are looking for, whatever we have in meter, is equals to what? Y in cm. Cross multiply, we are going to have x times 100 is equals to y. So we are going to multiply by 100. So multiplying this by 100 to get cm is like saying 10 raised to the power 2, right? Oh, don't worry, 100. So let's simplify. 100 is simply as 10 raised to the power 2. 18,000, 1.8 to standard form, right? To standard form, we have to take the decimal point this way: 1 2 3 4. So that is 1.8 times 10 raised to the power 4, positive, because we are going towards the left, times 10 raised to the power minus 5 times 10 raised to the power 2. So let's simplify. We're going to have 1.8 times 10 in brackets 4 plus minus 5 plus 2. 4 plus 2 is 6. 6 minus 5 is 1. So we're going to have 1.8 times 10, which is going to give us 18 cm. And that's our answer. Question 2 is a similar question to what we just solved, but instead now we're looking for the linear expansivity. Calculate its linear expansivity. So we just use our formula for linear expansivity as usual. Alpha is equals to change in length. What's our change in length? 40.05 minus 40. 40.05 minus 40 per unit length. The original length was 40 cm before it got longer, right? So meter rod of length 40 cm, that was the original length, times what? Change in temperature. The change in temperature is 20 degrees heated to what? 45 degrees. So 45 minus 20 is our change in temperature. 45 minus 20 is, let's just write 25 there to save us time. 40.05 minus 40 is 0.05. 40 times 25 is what? You can punch that to your calculator quickly. That is 1000. And so if we simplify, convert to standard form, we're going to have 0.05 is same thing as saying 5 times 10 raised to power minus 2. 1000 is same thing as 10 raised to power 3. Bring this up to change to minus, right? So we have 5 times 10 raised to power minus 2 minus 3. So our final answer is 5 times 10 raised to power minus 5 per Kelvin. That is the linear expansivity. Next question. The linear expansivity of a metal P is twice that of another metal Q when these materials are heated through the same temperature. Just reading like that, it looks very confusing, right? That's why you should learn to interpret this question. So the first line, the linear expansivity of a metal P is twice that of another metal Q. How can we interpret this? Okay, so from the question, this is what I can get from the question. It says that the linear expansivity, what's the symbol for linear expansivity? Alpha, right? Most times I forget how to write alpha. Oh my god, don't tell me I forgot how to write alpha. It happens sometimes. So linear expansivity of P is equals to what? 2 times is equals to 2 times the linear expansivity of Q. That's what the question stated. Let's read it again. The linear expansivity of a metal P is twice that of another metal Q. So it's 2 times the linear expansivity of Q, which you just wrote there. When these materials are heated to the same temperature, so temperature remains the same. Okay, temperature is the same. Their increase in length is also the same. Calculate the ratio of the original length of P to that of Q. So all we have to do now is to write out the formula. So the formulas are as follows. Change in length of P all over unit length of P times change in temperature is equals to what? 2 times change in length of Q all over unit length of Q times change in temperature. The reason I didn't write subscript Q here for this is because they told us what? The lengths are the same. The change in length are the same and the change in temperature is also the same. So we can cancel that out and we're left with what? We're left with 1 all over length of P, unit length of P, and 2 times 1, we have 2 all over unit length of Q. So what did I ask us to find? Calculate the ratio of the original length of P to that of Q. So the ratio of P to Q in length is what we're trying to find. So the ratio of LP to LQ is what we're trying to find. Okay, so to do that, we can cross multiply, just exchange LP and 2. So we have 1 over 2 is equals to LP over LQ. Therefore, the ratio is what? 1 ratio 2. This is our final answer. Okay, so on to the next question. Next question says that the ratio of the coefficient of linear expansion, if I say friction, of two metals, alpha 1 and alpha 2, is 3 ratio 4. We can pen that down. So the ratio of alpha 1 to alpha 2 is what? 3 to 4. if when heated through the same temperature, so temperature is the same in this question, the ratio of the increase in length alpha L1 over alpha, sorry, delta L1 over delta L2 is 1:2. So we're just going to write that down. So we're also given that delta L1 over delta L2 is equals to 1:2. What are we asked to find? The ratio of the original length L1 to L2 is what? Okay, so the best way to go about this question is to just take each of these, lengths as their ratio, to not to waste time, right? Or better still, let's just simplify this equation. So alpha 1 is linear expansivity of meta 1, right? So we have to write the linear expansivity of meta 1 out. So let's write it out. I should have used a different color for this so you don't get confused. Let me use a different color. And okay, let me just leave it like that. Okay, so for alpha 1, I'm going to write out the formula. Alpha L1, that is change in length of L1 over unit L1, that is L1, times change in temperature, which is the same for both, frankly speaking. I've done this, divided by linear expansivity 2. So linear expansivity 2, you can represent it change L2 over unit L2 times change in temperature. Last, everything will be equals to what? Everything will be equals to 3 over 4. So if we break down this equation, we know that change in temperature is the same, so we can strike that out first so we can have peace of mind. Then we can simplify. With division, we can just multiply this on this. So L1 times L2 roots. Okay, we're already done with that because I've cancelled that out. And then L1 times change in temperature 2. Okay, so we simplified it, and this is what we arrived at. Now L2 over L1, remember it was what? L1 to L2 is 1:2. Therefore L2 to L1 is going to be what? 2 to 1. So in place of L2, we can just write, in place of L2 we can just put 2 there, and in place of L1 you can just put 1. And if you remember our question, What did I do? I substituted the wrong one. In place of change in L2, we put 2 there. And in place of change in L1, we put 1 there. Right? Because L1 equivalent to 1, L2 is equivalent to 2. That's why we're able to substitute like that. So if I remember the question very well, let's look at it. They said the ratio of the original length L1 over L2 is what? So we're looking for L1 over L2. We just have to simplify. 1 times L2 is L2 over L1 times 2 is what? 2L1, right? Is equals to 3 over 4. We can take this up. We can take the 2 up. So we're going to be left with L2 over L1 is equals to 2 times 3, which is 6 over 4. And then we invert. This is L1, right? Then we invert. That is L1 over L2 is going to be equals to 4 over 6. 2 here, 2, 2 here, 3. So our answer is 2 ratio 3. The only reason I'm wasting time solving is so you can understand, so I don't jump steps. That's why I'm taking time to write clearly so you can see my work. In JAMB, you have less than a minute to solve this question. So when solving, be fast about it and keep your work organized so you don't get confused or you don't get lost. Okay, so on to the next question. The ratio of the coefficients, okay, I've done that. Number 5, a piece of brass of mass 170 kg has its temperature raised from 0 degree. Calculate its volume, its increased volume, given the density of brass. Okay, so that's volume expansivity, right? And I promise to go into some detail about volume expansivity. Now in volume expansivity, we have another formula. The formula is as follows. So volume expansivity, gamma, is equals to the sum of apparent, which is represented by A here, apparent volume expansivity plus apparent volume expansivity of the container. So from that question, we're given mass, 2 different masses, and we're also given, number 5, calculate the volume given the density of brass. So they give us the density of brass and they give us the mass of brass, which means we can find the volume of brass as well. So this question is normal case of volume expansivity. Why this has to do with what I just talked about. So let's solve the question anyways. Number 5, before we come back to this, let's solve number 5 first. So number 5 says a piece of brass of mass 170 kg. You can just write down the parameters. Temperature is 30. That machine temperature is 30. 30 minus 0 is 30. So calculate its increase in volume. Increase the volume, calculating its change in volume. So that's delta V. Right? So we're looking for delta V. Given that density, so We can write our change in temperature as 30, our change in volume, which we are looking for, density of brass at 0 degrees is 8.5 times 10 raised to the power 3. So density is equals to 8.5 times 10 raised to the power minus 3. And then what else? Oh, 10 raised to the power 3, not minus 3. Then its cubic expansivity is 5.7 times 10 raised to the power minus 5. Cubic expansivity, the symbol is gamma. What would you see just now? 5.7 times 10 raised to the power minus 5 times 10 raised to the power minus 5. That is our cubic expansivity. Our density, remember, it's raised to the power 3. Okay, so what's our formula? Well, I'm looking for change in volume, right? Our formula for cubic expansivity is given by change in volume, which we're looking for, per unit volume, that's the original volume, per degree rise in temperature. So, well, this is very straightforward. If we make volume such a formula, cross multiply. So I'm multiplying our linear expansivity by what? The initial volume times what? Change in temperature. Our linear expansivity is 5.7 times 10 raised to the power minus 5 times V. V is what? We don't know what V is. The initial volume, we can calculate it from the mass given and the density given, because density is equals to mass over volume. Therefore, volume is going to be equals to mass over density. So using the mass, 170 all over density, which is 8.5 times 10 raised to the power 3. We can just put it there like that and hopefully something will cancel out. So 170, I'm teaching you how to save time in JAMB. 10 raised to the power 3, right? Times what? Change in temperature, which is 30. Okay, so we can simplify everything together. Now, change in volume is going to be equals to, how do we simplify this in the easiest way possible? We can start counting out all the zeros we can find. So cancel this 0 here, we're going to be left with 2. Cancel this 0 here, we're going to be left with 1, right? So we're going to have 17 times 3 all over 8.5 times 10 raised to the power 1. So 8.5 times 10 is 85, obviously. 17 times 3 divide 85, that's what we're finding. 51, so 17 times 3 is 51. 51 divided 85 is 3 over 5. Honestly, I just need the decimal. 0.6. 0.6 times 5.7. 0.6 times 5.7. We're going to get 3.42. So 3.42 times 10 raised to the power minus 5 meter cube. That's our answer. If all we did is correct, that should be our answer. Except this was supposed to be raised to the power minus 3. But what we're given our question is raised to the power 3. So we used it like that. Okay, next question. A density glass bottle. Okay, back to the case I was talking about. Another formula for cubic expansivity is this. Apparent plus the expansivity of the container. Another way to look at it is, okay, so this is the real cubic expansivity, right? Another look at it as this. Real is equals to apparent plus the expansivity of the container. You can just look at it like that. what does this mean? It means that, let's say you have a container and you have liquids, some liquids inside. I don't know what's inside. And this is the initial volume. We can just mark the initial volume as, let's say, V1, right? Hitting this container, on hitting this container, put fire, you hit the container. On hitting this container, not only the liquid will expand, the volume of the container, that is the container, will also expand. So with the container expanding, you can expect the volume of the liquid to initially drop down, and later the liquid then expands to fill that space which the expanded vessel has created. So the concept is this liquid inside will not increase in volume normally, say from V1 to V2, because the vessel is also expanding. That means we need to account for both the cubic expansivity of the container and also add it to what we apparently saw. So if we measured that it increased from V1 to V2, that is the change in volume, that's just what we saw, but that's not true. That's not the truth, because we didn't account for the expansion of the container as well. So this is what we call apparent expansivity, the apparent cubic expansivity, while the expansion of the container itself is called the expansivity of the container. Right? Now, to find the real cubic expansivity of the liquid, we have to account for both the container and what we saw. Now, formula for apparent cubic expansivity is given by, please take note of this formula, mass of liquid expelled all over mass of liquid remaining times temp change times temperature rise or temperature change. I can just write it as times temperature change. Now, it could be mass of liquid expelled over mass of liquid remaining times temperature change, or it could be volume of liquid expelled over volume of liquid remaining times temperature change. So let's solve that question. Number 6. A density bottle contains 44.2 gram of a liquid at 0 degrees Celsius and 42.02 at 50 degrees Celsius. Calculate the real cubic expansivity of the liquid if the linear expansivity of glass is given as 1 times 10 raised to the power minus 5. Okay, this is really straightforward. First of all, we're asked to calculate what? Cubic expansivity, and we're given linear expansivity. That means we have to convert linear expansivity to cubic expansivity, right? So the real cubic expansivity of the liquid, we're given the cubic expansivity of glass. Our formula states that what? Apparent cubic expansivity plus cubic expansivity of the container, which is in this case glass, will give us the real cubic expansivity we're looking for. So if we are to write out our formula, real is equals to apparent. Apparent, we have to solve using this formula, and then we add it to the cubic expansivity of glass, right? Remember that the relationship between linear and cubic expansivity is what? Cubic expansivity is 3 times linear expansivity. So if we're given linear expansivity for glass, we have to what? Multiply by 3 to get the cubic expansivity. Okay, so let's get into it. Y arrow, which is real cubic expansivity, is going to be equal to what? The apparent cubic expansivity. So how do we get the apparent cubic expansivity? We're given what? Mass of liquid, right? So okay, so the concept is that if you have a 44.25 gram liquid, right, at 0 degrees, and then at 50 degrees you just have 42.02 grams left. What does this mean? It means that some of the liquid have been lost, right? That's mass expelled from our formula here, mass of liquid expelled. So to calculate that, we have to subtract. So 44.25 minus 42.02. 44.25 minus 42.02 all over the mass remaining. The mass remaining is what? 42.02 at 50 degrees. Times degree rise in temperature. So the rise in temperature is from 0 degree to 50. So 50 minus 0, that's 50, right? If we were to simplify, remember we're calculating our apparent cubic expansivity first before anything else. So our final answer is going to be 44.25 minus 42.02 equals to 2.23 all over 42.02 times 50. That is 2101. Just divide 3 2101. That's 1.061 times 10 raised to the power minus 3. Okay, so now we have the what? Apparent cubic expansivity. Let me make some space. So remember our formula was that the real cubic expansivity is equals to apparent cubic expansivity plus what? Cubic expansivity of the container. So to calculate the real cubic expansivity, we already got what? Our apparent, so we can just write that there. 0.61 times 10 raised to the power minus 3 plus what? Our cubic expansivity of the container. In this case, the container is what? Glass. So they give us the linear expansivity as 1 times 10 raised to the power minus 5. So the linear expansivity, if the linear expansivity is 1 times 10 raised to the power minus 5, and gamma is equals to 3 times the linear expansivity, therefore our gamma is going to be what? 3 times 10 raised to the power minus 5. So times 3 times 10 raised to the power minus 5. Now we just have to add this to get our final answer. Most students make these mistakes when adding. You cannot add two unlike terms. You see 10 raised to the power minus 3 here. You see 10 raised to the power minus 5 here. You cannot add them together because they are unlike terms. How can we add them together then? You have to make them like terms, right? And how do we go about that? So first of all, 10 raised to the power minus 5 is smaller than 10 raised to the power minus 3. So I think the best way to go about this is to make 10 raised to the power minus 5 10 raised to the power minus 3. And how can we do that? How can we do that? We have to what? Reduce the decimal places. Abi? So 1, 2. If we remove 2, we're going to be left with 10 raised to power minus 3. So we have what? 0.03 times 10 raised to power minus 3. If you want to get our 10 raised to power minus 5 back, 1, 2. Add that 2 to the minus, that is 10 raised to power minus 5, Abi. So that's how I came about that. So 1.061 times 10 raised to power minus 3. Since they are like terms now, we cannot add these together. So 1.061 plus 0.03 is going to give us 1.1 approximately. But let's just write 1.091 times 10 raised to power minus 3 per Kelvin, and that's our final answer for the real cubic expansivity. Number 7, what is the quantity of heat that will be given out if a bar... Okay, so we have entered on that topic. This topic is where we treated heat capacity and specific heat capacity. So let me just give you a brief rundown of what the topic entails. So heat capacity. Formula you should know as follows. Quantity of heat, that is heat energy, is equals to specific heat capacity, or rather mass times specific heat capacity times what? Change in temperature. That's one formula you need to know. And that formula you need to know is that Q, quantity of heat, that is heat energy, is equals to heat capacity times change in temperature. There are two different things. So specific heat capacity is the amount of heat that is lost or gained per unit kilogram. Unit for mass is kilogram, right? For every degree rise in temperature. While heat capacity is the mass of heat lost or gained for every degree rise or fall in temperature, irrespective of mass. So heat capacity does not depend on mass, but specific heat capacity is dependent on mass. And most of the time, this is the most popular formula we use. This one is the most popular. So this is the formula we make use of most of the time. But it's also helpful to know that there's a formula for heat capacity as well. Now, the relationship between heat capacity and specific heat capacity, from what we can see here, the relationship would then be to like equate what is common between them. So what is common between them? Temperature. Change in temperature is common. So we can make change in temperature subject in both sides. So Q over MC is equals to change in temperature. Make change in temperature subject here. We have Q over H is equals to change in temperature. So because they have that in common, we can equate both of them. So Q over MC is equals to Q over H. Right? So cross multiply, we're going to end up at H is equals to MC. Q cancels out. Now take note of this formula as well. So H is equals to MC. What does this mean? It means that if you're asked to calculate heat capacity, you can calculate heat capacity from specific heat capacity. So heat capacity is equals to specific heat capacity times mass. While this is the main formula, this topic is very easy actually, and you'll find out why soon. So let's take that question. Number 7. What is the quantity of heat that will be given out of a bar of brass of mass 350 gram? Is cooled bar of brass of mass 350 gram if it is cooled from 95 degrees Celsius to 20 degrees Celsius. Specific heat capacity. So they're asking of what the quantity of heat is. What's our formula? Our formula is quantity of heat equals to mass times specific heat capacity times change in temperature. So that's all we're going to do. Multiply the mass. Remember to convert mass to kilogram. So anyway, so mass is equals to 350 gram divided by 1000. We're going to get what? 0.35 kg. Right? Specific heat capacity, as given your question, is what? Our specific heat capacity was given as 380 joule per kilogram per Kelvin. So 380. And then what again? We're given change in temperature. It's 95 to 20 degrees Celsius. So that is 95 minus 20. 95 minus 20 is going to give us 75. Am I right? So our change in temperature is equals to 75 degrees Celsius or Kelvin. Now, I don't know if I've mentioned this already, but change in Celsius, change in degrees Celsius is equals to change in Kelvin. So you don't need to convert again. What do I mean by this? I mean, like, if normally the formula, the unit of specific capacity is joule per kilogram per Kelvin. So please think that since you were given temperature in Celsius, you need to convert temperature to Kelvin first before getting your change in temperature. But that's not the case because change in Celsius is equal to change in Kelvin. So it will be a waste of time. Let me prove to you that change in Celsius is equal to change in Kelvin. Let's say, for example, what we just subtracted. We subtracted 95 degrees minus 20 degrees, right, to get 75 degrees. If we're to convert to Kelvin first, we have to add 273 to convert to Kelvin. So 95 plus 273, we have converted 95 degrees Celsius to Kelvin, minus what? 20 plus 273 Kelvin, we have converted 20 degrees Celsius to Kelvin. So if we subtract now, we're going to be left with 95 plus, you open the brackets, minus 20, right? Or let me not confuse you. Let me just follow it accordingly. So 273 minus 20 minus 273 after opening the bracket. You see that 273 minus 273 is equal to 0. So you are still left with what? 95 minus 20, which is the same thing that we're going to get at the end of the day. So change in Kelvin is also change in Celsius. Okay, let's have a question. So we asked for quantity of heat. Our formula is MC change in temperature, right? So our M is what? 0.35 kilogram times 380 times what? 75 Kelvin, and that's going to give us how many joules? That's the unit for energy. 9,995 975 joules. 9,975 joules. That's our answer. for the quantity of heat which will be given out. So number 8, calculate the final temperature of 2 kg of alcohol at 25 degrees when 20,160 joules of energy is added to it. Okay, so we're asked to calculate final temperature. We know where this is going, sha. First of all, let's calculate change in temperature, then we can use that to calculate final temperature, right? So we're given specific heat capacity, we're given the energy, and we're given mass. So we can find change in temperature. So mass is 2 kg. Mass is 2 kg. The initial temperature is 25 degrees. Energy is 2160. And alcohol has a specific capacity of 2,520 joules per kilogram per Kelvin. So I'm just going to write specific capacity as 2,520. Alright, and we're given our energy, that's the quantity of heat in joules, as 20,160 joules. And then what's left? We're given our initial temperature as 25 degrees Celsius. So our formula states Q is equals to what? MC, change in temperature. So Q is 2160, and then M is 2 kg times C, which is 2520, times change in temperature. So we can calculate change in temperature now. So change in temperature is equals to 2160 all over 2 times 2520. I'll just press my calculator for this, so we don't waste time. 2160 divided by what? 2 times. Okay, this is an issue, a very, very big issue for JAMB students. Please don't just go and press your calculator. 2160 divide. This is how it will be like your calculator. 2160 divide 2 times 2520. Sometimes you might get a wrong answer. So this is what I advise for you students. Do things singly. Solve what is under separately. Solve what's at the top separately. The final answer you get, divide that at the top by that at the bottom. So 2 times 2520, you have to do that first, just to be safe. 2520, divide that first. Simplify that first. So 2 times 2520 is what? 5040. So we are dividing 20,160 over 5040. 5040, and that's going to give us 4 on the dot. So our change in temperature is 4 degree Kelvin or Celsius. Anyone? 4 degrees Celsius. And since our change in temperature is 4 degrees Celsius, remember that change in temperature is equals to theta 2 minus theta 1, right? That means change in temperature is equals to, this is our initial temperature. Was it cooled or was it? So the final temperature of a 2 kg. Okay, calculate the final temperature, right? 25. When this amount of energy is added to it. Now when we add energy to a substance, it should increase in temperature. So we expect the final temperature to be higher than the initial temperature. Don't forget that concept. If we remove energy from it, it should decrease in temperature. So the final temperature, we can expect it to be lower than the what? Than the initial temperature. So we expect that the temperature we are getting as the final temperature is higher than 25 degrees Celsius. So that's why we have what? Theta 2 here and minus 25, because we expect that the final temperature is higher. But if it were lower, we'll put theta 2 as 25 and we'll put our theta 1 as the lower temperature. So you get the concept. So our changing temperature is what? 4 degrees Celsius. So 4 is equals to what? Theta 2 minus 25. Move 20 minus 25 to the other side. So our final temperature is what? 4 plus 25, which is equals to 29 degree Celsius. So if I'm to interpret this question and the answer I've gotten, it means that when we added 20,160 joules of energy to which body? Okay, to alcohol, it increased from 25 degrees Celsius to 29 degrees Celsius. That's the interpretation. But this is a lot of energy for just that small increase in temperature. What kind of slavery loss of energy is that? Anyways, you get the point. Number 9, 500 grams of water is heated so that temperature rise from 30 to 72 in 7 minutes. Calculate the heat supplied per minute. Okay, so this question is kind of tricky. Calculate the heat supplied per minute. This per minute. It just means that we are calculating our answer in joule per minute, right? And at the end of the day, we are supposed to divide our answer by about 7 minutes. That's just what it means. So it's nothing too much. We just use our normal formula for quantity of heat, which is Q is equals to M, right? C times change in temperature. That is the formula we just use. And the quantity of heat we get, we just divide it by the time. 7 minutes. As easy as that. So let's go about it. 500 grams of water, change it to kilogram is 0.5 kg. Change the temperature, 72 minus 30 is what? 72 minus 30 is 42. 42, then 4200 for heat capacity. Specific heat capacity, rather, to be precise. Okay, we have reached the end of the page. I need to create space. So what's the mass? The mass is, if I recall very well, the mass was given as 500 gram. So 500 gram, if you convert that to kilogram, we have 0.5 kg. Our specific capacity was given as what? Was given as 4,200, which I called 4,200 joule per kilogram per Kelvin. And then our quantity of heat is what we are looking for. We're also looking for that. We're also looking for what? Mass. Okay, we got mass. MC, change in temperature. So our change in temperature, we'll calculate it as 42 degrees Celsius. So applying the formula, Q is equals to MC, change in temperature. We're going to be left with 0.5 times specific 4200 times change in temperature, which is 42. This is slavery, man. We're going to get energy. So energy per minute, that is joule per minute. I have to divide it by what? The time given. The time given was what? 7 minutes. So we'll divide by 7. How do we simplify this? Now I was expecting something to cancel out. Why did they purposely make temperature 42 to match with this? Anyway, let's solve. So 0.5, just multiply your calculator. Don't waste time. 4,200 times what? 42 is equals to 88,200. 88,200 divided by 7. 88,200 divided by 7 is what? 12,600. So the energy per time, or the heat energy per minute rather, is what? 12,600 joules per minute. That's our answer. Number 11. Observe this, observe this. 1.2 kilowatts immersion heater is used to supply energy for 75 seconds. The energy supply is used to heat 800 grams of paraffin in a calorimeter of heat capacity 42. Okay, so questions can get confusing when you just read them directly. You just have to write out their parameters. So first of all, we're given kilowatts. This is power. Power. One thing I need to know is power. Formula for power is equals to what? IVT. Am I right? No, I'm not right. Power is equals to work done over time. So work done is IVT. Over time should cancel out. Right? So I want to know that heat energy has alternative formulas, right? They have alternative formulas. What that is energy. Means any formula for energy can be used. Let me tell you what I'm talking about. So Q is energy, quantity of heat energy, right? Energy has different formulas. So we did work, energy, and power. Energy can be mgh, right? Energy, that is energy during free fall, energy lost or gained during fall, mgh. Energy can be in electricity, energy can be ivt, current times voltage times time, energy. Energy can also be v squared t over r. This is another formula for energy. Energy can also be I square RT. So all these things I'm showing you are formulas for what? Energy. These are all formulas for energy. Now that means power, since power is work done over time, or power is equals to what? Energy over time. So by extension, the formulas for power will be what? Divided by time. So we can have power formula as what? Mg over time, right? We have mgh over time. And we can have what? Ivt over t. So another formula for power is what? Iv. Then we can also have v square r all over time. Time cancel out. So another formula we have for power is what? V square over r. So we have v squared over r. Another formula for power is what? I squared r divided by time. So take note of this. Though we're still going to revisit it when we do electricity. But these are formulas you should take note of. So in our question, let me clear some space. So in our question, they said 1.2 kilowatts. Kilowatts just tells me this is power, right? 1.2 kilowatts heater is used to supply energy for 75 seconds. What does that tell me? What does that tell me? Since power is equals to work done over time, or energy, or like power is equals to energy, heat energy over time, then heat energy is also equals to power times time. So I have to multiply that power multiply by the time to get the what? Heat energy supplied by the heater. So 1.2 kilowatt immersion heater is used to supply heat energy for 75 seconds. The energy supply is used to heat 800 gram of paraffin in a calorimeter of heat capacity 42.5 joule per Kelvin from 20 to 66. Calculate specific heat capacity of paraffin. So first of all, let's find what the energy supplied is. So they said 1.2 kilowatts, right? 1.2 kilowatts times time for how many seconds? 75 seconds was how long? So multiply by 75 seconds. Kilowatt, kilo means 1000. So we have what? 1.2 times 1000 times 75 to get our answer in joules. So 1.2 times 1000 times 75, get our answer in what? Joules, which is 90,000 joules. Now we can equate that 90,000 joules is equals to MC change in temperature. What is the mass given? The mass given was 800 gram. 800 gram to kilogram is 0.8 kilogram. And the heat capacity, okay, they give us heat capacity and they give us specific heat capacity. We have to look for specific heat capacity. So change in temperature was given as well, 20 to 66. 66 minus 20 is 46. So we have 46 as our change in temperature. The mass was given as 0.8 kilogram. So we can use this to find what specific heat capacity. So C is equals to 90,000 all over 0.8 times 46. So 90k divide 0.8. Remember I told you to do the denominator separately. So 0.8 times 46 is 36.8. So 90,000 divides 36.8 is 2,445.7 per kilogram per Kelvin. This is our answer. Now while solving, I actually realized that we had a relationship between specific heat capacity C and what? Heat capacity. What was the relationship? Heat capacity is equals to what? MC. That means they give us heat capacity and they give us mass, which means with that alone we should have been able to find what the specific heat capacity is. Let me see something. So 42.5 divided by 0.8, which was our mass. And we're getting something else. Okay, a calorimeter of heat capacity. Okay, so this might look a little bit confusing But please don't be confused though. Like, okay, so where the confusion is they give us the heat capacity of the calorimeter which the paraffin was placed in, right? Usually the heat capacity of calorimeter is taken to be negligible, but in this question it actually has heat capacity. So the fact that it has heat capacity, it means that the calorimeter, some energy from the immersion heater is going to be lost to the calorimeter before reaching the paraffin to start with. Do you get the point? So how do we go about this? First of all, you have to calculate the energy of heat which is lost to the calorimeter. Then the remaining energy is what will be used for the paraffin. Okay, so let's do that. Now, if you could recall the formula, heat capacity Q is equals to heat capacity times change in temperature. You would understand that this is very, very clear. Where did we treat that? Was it under here? Oh, I wiped it off. Okay, I wiped it off. So if you have been taking notes, you would remember where I said heat capacity is different from specific heat capacity. So we're actually given heat capacity of the calorimeter. So to calculate the quantity of heat which was lost to the calorimeter, we use this formula. So the heat capacity of the calorimeter is what? 42.5 times what? Change in temperature. Change in temperature from what? 60 to 20. 20 to 66 rather. That is going to give us 46. So times 46. So 42.5 times 46 is 1955. So 1955 joules was lost from the immersion heater. So what amount of heat actually supplied by the immersion heater to start with? First of all, quantity of heat equals to power times time, right? And power given was what? 1.2 kilowatts times what? Time is around for 75 seconds. Kilo means 1000. So 1.2 times 1000 times 75. What did we get then again? We got 90,000. So 90,000 minus this amount of heat that was lost. So 90,000 joules. So 90k minus 1955 is equals to 88,045 joules. So this is the formula. This is the heat energy which was actually used to heat up the paraffin. So this is the one for the paraffin. This is the one that heats up the paraffin. This was the one that was lost. This one was lost to the calorimeter. Therefore, the total energy, this one is the total energy generated from the heater. Energy from heater. So the energy generated from heater minus the energy lost from the calorimeter will give us the energy which was used to warm the paraffin. So that means we are going to use what? 845 is equals to what? MC theta. Mass was, if I can still remember, no, I can't remember. The mass was 800 grams divided by 1000, that is 0.8 times what? Specific heat capacity was given as, for paraffin, that's what we're looking for, right? And we have changed the temperature as 46. So specific heat capacity is going to be what? 88045 over 0.8 times 46. 0.8 times 46 is 36.8, and so 88045 divided 36.8 is 232,392.5 joules. Sorry, 0.5 joule per kilogram per Kelvin. This is our final answer. So I've solved this question. The temperature of water from tap A and B are 25 degrees Celsius and 75 degrees Celsius respectively. So how do we go about this problem? Now, this problem is a case of conservation of heat. This number 12 we're about to solve is a case of conservation of heat. If heat is conserved and neglecting all factors, then there is a law of conservation of heat energy that states that the total heat that is gained must equal the total heat that is lost. And we'll see how we apply it. Okay, so let's apply. Total heat gained for number 12. Let's come down. Temperature of water from tap A and B are 25 and 75 degrees Celsius respectively. If a mixture of water at 40 degrees Celsius is required, calculate the ratio of the mass of water. Wait, so we're already at ratio. Okay, calculate the ratio of mass of water from tap A to that of tap B. Okay, so this is how we go about it. If you mix two liquids of different temperature, let's say 2 cups of water together, there is something that happens. The hotter one would reduce in temperature while the cooler one will increase in temperature, and they will both meet at a balanced point, which is the final temperature, a final steady temperature, or an equilibrium temperature. So what does that tells us is that from our formula of Q is equals to MC, change in temperature, it means that our change in temperature would include theta of hot water, right, minus theta, that is the final temperature. Because the final temperature will be what? The final temperature will be less than the temperature of the initial hot water. And then for the cold water, it's going to be what? The final temperature minus the initial temperature of cold water, because the cold water will get warmer when you mix it with hot water, abi? So that's the change in temperature. Now, the total heat gained from cold water is equal to total heat lost from the hot water. That's the concept. In this case, the total heat lost from the hot water, from theta hot to the final steady temperature, is equal to the total heat gained by the cold water from the cold temperature, initial cold temperature. It gained heat to a final steady temperature. So that's the concept. So let's finish the formula. So since mass of water, okay, the mass might be different, right? So we can just use the terms. I can just use mass for the hot water, and then I can use m mass of the cold water, right? Right. So that's it. What about specific heat capacity? Some of you may ask. Now, since the liquids are the same, if the liquids are the same, we can cancel out the specific heat capacity, and the main formula will now be mh theta hot minus final temperature is equals to what? Mass of cold water bracket what? Theta final temperature minus cold temperature. But note that if the liquids are different, specific heat for both liquids should also be different, and you have to use it in the formula. So from our question, let's just use this formula right here and solve. So the mass is number 12. The temperature of water, tap A, 25 degrees and for tap A and 75 degrees for tap B. Okay, so tap A is the cooler temperature, tap B is the hotter one. So we're asked to calculate the ratio of the mass of water from tap A to that of tap B. Remember, tap A is the hotter one. Is the cooler one, right? Tap A and B. The temperature of water from tap A are 25 degrees, right? And from tap B is what? 75 degrees. So tap B, hot water is rushing from tap B. Tap A, cold water is rushing from tap A. So that means to calculate the ratio of the mass of water from tap A to that of tap B if the final steady temperature after they have mixed is what? 40 degrees Celsius. So we can apply the formula straightforward. I have to wipe some things here. So remember that tap A was what? The cooler temperature. So mass of cold water, MC. Theta final was what? The final steady temperature was what? 40 degrees Celsius. No need to put in it. Minus what? The cool temperature was 25 degrees. Similarly, on this side, the hotter temperature was what? Theta hot was what? 75 degrees Celsius minus the final steady temperature, which is 40. And then the ratio of the masses, m hot to what? Equals to. So the ratio of tap A to that from tap B. So I'm looking for the ratio of cold to hot because tap A is cold, right? So to find that, we have to what? Divide both sides by mh or let's just simplify first. This one I'm solving backwards, so God help us. So 40 minus 25 is 15. Am I right? So 15 mc is equals to 75 minus 40 is what? 25 or it's 35. So 35 hot. So I'm looking for the ratio of cold to hot. Therefore, we just, how can we find cold to hot? We can divide both sides by what? mh, right? So divide by mh, divide by mh, divide by 15 to remove 15 from here, divide by 15, 15 cancel, 15 cancel, 1 left, 15 here, and 15 here is what? Okay, it cannot go. So we have 5 here as 30 as 7, and then we have 5 here as 3. Right? Then m hot cancel m hot. Therefore, we are left with what? mc over m hot is equals to 7 over 3. Therefore, the ratio is what? 7 ratio 3. And this is the answer. Oh, there are options. So this is the correct answer. Okay, so number 13 is a special case. Two metals XY lose the same quantity of heat. That just tells me that Q is the same for both, right? That means I can equate the formulas for both. If Q is equals to MC, change in temperature, mass of X is, I'm going to represent by MX, right? And specific capacity of X, CX. Then I will represent that for Y as what? My and not Cy as well, changing in temperature. So we can equate both of them since the energy, the quantity of heat is the same. So let's move on. What did they say? Temperature drops 25 to 20. So changing temperature is 5 degrees. If the specific capacity of X is half that of Y, specific capacity of X is half that of Y. So we are saying Cx is equals to half that of Y. It's also Cy over 2. Right? So this just tells us that cross multiply, I have 2Cx is equals to Cy. So in place of Cy, we can just put 2Cx there. I'm going to wipe off Cy and put 2Cx. Cx. Okay. Remember that this is for x side and this is for y side, right? We can equate them because their heat energy is the same. So what are they asking to look for? Ratio of the masses of x to that of y. Okay, so they're asking us to look for what? Mx over my. So how do we find mx over my? First of all, change of temperature is the same for both as well. If you noticed, change the temperature is also the same, so we cancel out. And then we have what? 2mycx left, right? And we're looking for mx over my. So how do we make mx over my? We divide both sides by, wait, something else can also cancel out. What can also cancel out? Cx can also cancel out from both sides. And we're left with what? 2my. Mx equals to what? 2my. Therefore, ratio of mx to my is what? 2 over 1. So the answer is 2 ratio 1. Okay, answer is 2 ratio 1. 14. A piece of copper of mass 20 grams at a temperature 110 degrees was dropped into a mixture of ice and water at 0 degrees Celsius. When I heard ice, whenever you hear ice or steam, just know that it has to do with latent heat. Okay, so I've not talked about latent heat yet, but the formula is very straightforward. We have two types of latent heat, or it could be more, but the most popular ones are latent heat of vaporization and latent heat of melting or freezing or fusion. So we have two types: vaporization and fusion. Fusion is also called melting. So regardless of what type of latent heat, the formula is given as what? Q is equals to ml. L is latent heat. L represents latent heat. L represents latent heat capacity. While Q is the energy lost or gained. Latent heat is usually energy lost, So yes, loss or gained. Conversion from vapor to liquid. Yes, you can make use of latent heat. So amount of energy gained or lost during change of states is called latent heat. Now, latent heat can only occur at the same temperature. So if ice changes to water, this change of state occurs at the same temperature of 0 degrees Celsius. So the question is now, what caused the change of state from ice to water? It is what? Latent heat of fusion. Fusion also means what? Melting. Now for vaporization, from liquid to vapor, or we can take an example of a liquid, which is water. From water to steam, this is change of state as well, right? So what causes this change of state? It is latent heat of, and it occurs at what temperature? 100 degrees Celsius. Latent heat of what? Vaporization. And it occurs at the same temperature. So I've emphasized that what you need to note is what? Formula. Q equals ml. So let's use that to solve. Okay, so the question number 14 says a piece of copper of mass 20 grams at temperature. So this can get really confusing, but there's an easy way to go about it. You just have to divide your page into two sides. Now let me tell you what the division is for. So I'm just going to draw a straight line. On one side, we are going to only consider the masses that are gaining heat. And on this side, we're going to only consider the masses that are what? Losing heat. Okay, so let's go. A piece of mass of copper of mass 20 grams, temperature 110 degrees, was dropped into a mixture of ice and water. This just tells me that copper is clearly hotter, right? Copper is going to be losing heat. So I'm going to place copper on the losing heat side. So copper is hot. It's going to be losing heat when you drop it inside water. Then the water is going to gain heat from copper. So copper is in loss side. Why what? Water and ice, they are in the gaining side. Let's use a different color. So water and ice, they are gaining heat. Okay. Now, because I saw ice there, ice can only change to water when it absorbs latent heat. So ice can only change to water when it absorbs latent heat. That is why if you place ice on your body, the reason it feels cold clearly is because the temperature is at 0 degrees, yes. But on changing state to water, it absorbs latent heat of fusion from your skin, which gives you that cold sensation. Same thing with spirit, methylated spirit. If you pour methylated spirit in your body, it absorbs latent heat of vaporization and then changes to gaseous form. That will give you that cold sensation for spirit, even when spirit is at room temperature. And that's a clearer example. So because ice is here, we know we're going to make use of latent heat of fusion, and they gave us that parameter here. So that being said, let's analyze. First of all, let's write our parameters. Okay, final steady temperature is 0 degrees, fine. The amount of ice that melted, that's what we're calculating. So we're calculating mass of ice that melted. We're also calculating, so we're given mass of copper, 20 gram, and it was at a temperature of 110 degrees Celsius. So the mass of copper was given as 20 gram, and the temperature of copper, let's call it theta C, so 110 degrees Celsius. Is that all, everything about copper? Copper has a specific heat capacity of 0.4 joule per kilogram per Kelvin. So C of copper is 0.4. Is that all about copper? Okay, so that's all about copper. Now next, let's talk about water and ice. They don't give us the mass of water, or they don't give us the mass of ice. They only give us the specific latent heat of fusion of ice. So they give us specific latent heat of fusion. So latent heat. So latent heat of fusion of ice was given as what? 330 joule per gram. And the temperature of ice was what? Whatever you do in this life, do not ever forget to look at what you are asked to calculate. They're asking us to calculate the amount of ice that melted. The amount of ice that melted. No additional energy is needed to convert ice to water at 0 degrees. Therefore, we don't even need, that means no energy was lost from the copper that was dropped into the mixture of ice to convert it to water. The only situation where energy will be lost is if, okay, the water now increased in temperature from 0 degrees. That is when additional energy was used from the copper. But only specific latent heat of fusion of ice was used, which is 330 gram, and we can use that to find our answer. So joule per gram, 380 joule per gram. Remember, since Q is equals to ml, and then quantity of heat lost is equals to quantity of heat gained. So for copper, the heat generated by copper is equals to mc change in temperature. So don't forget that normally you are supposed to add Q is equals to mc change in temperature, but no heat was lost from copper to the ice. If not, there would have been a change in temperature. The initial temperature was 0. The final temperature is also 0. 0 minus 0. 0 through all this, everything is going to be 0. So the only heat gained by the water, by the ice, is Q equals ml, which is specific latent heat. Therefore, we're going to equate ml is equals to what? mc change in temperature. This m is what? Mass of, let's just call it mass of ice that melted. mc, let's make m sub c to represent mass of copper. So mass of ice that melted is given by what? The mass of copper, which is 20 gram. Okay, 20 gram to kilogram divided by 1000 is 0.02 kg times C, 0.4 times what? Change in temperature. 110 minus 0, which is the final steady temperature, is 110. All over the latent heat, L, which is given as what? 330. So 0 cancel 0. Just multiply this in your calculator. We're going to arrive at, so 0.02 times 0.4 times 11 is equals to 0.088 all over 33. 0.088. No. Okay. And I wrote, so 0.088 all over 33. But wait, this was given in joule per gram. That means there was no need to convert. Please make sure your unit is uniform. Since our mass was given in gram here, and our specific heat capacities were also given in gram, that means we can use the gram without converting. Don't go and get a wrong answer in exam. These are the things you should look out for. So instead of 0.22, we're going to have 20 gram. Yeah, so 20 times 0.4 times 11 is equals to 88. So I was supposed to have 88 over 33. 88 divided by 3 is 2.66 or 2.67 gram. So that is the mass of ice that melted. Next question. Ice of mass 50 gram at 0 degree was completely melted by 70% of the total heat energy supplied. Calculate the total heat energy supplied. 70% of the total heat energy. Specific latent heat. Okay, so we're only given specific latent heat of fusion, which means we just have to apply our formula for specific latent heat, which goes like this: Q is equals to ml, and they said 70% of the total energy. So let's assume Q total is what gave ml, right? And we're asked to find what? We're asked to find the total energy supplied. Mass of ice 50 grams at 0 degree, completely melted, heat of fusion 336. So mass was given as 50 gram. Times what? Latent heat of ice is what? 336 joule per gram. Since gram and gram they are uniform, we can use it like that convert it to kilogram. So 50 times 336 is what? So 16,800 joules. 16,800 joules is 70% of QT. 70% is 70 over 100, right? So 70 over 100 QT is equals to 16,800 joules. 0 cancel 0. So we have 0.7 because 7 divided 10 is 0.7. QT is equals to 16,800 joules. QT, that is the total energy, would therefore be what? 16,800 divided 0.7. Okay, and that gives us 24,000, which is our final answer. 24,000 joules. Okay, so next question. A piece of copper of mass. Oh, there's an option. So this is the correct answer here. Next question, 16. A piece of copper of mass 300 grams at temperature 950 degrees is quickly transferred in a vessel of negligible. Okay, so this is very, very long. Like, I'm already getting tongue twisters just reading this. The easiest way to answer a question like this is to draw a straight line, separate the masses that are gaining heat from the masses that are losing heat. So I'm going to draw a straight line. So those that are gaining heat will be on this side. Those that are losing heat and let me just say gaining and then losing. I just need some space. I just need some space. So copper of mass 300 grams at temperature 950 degrees Celsius quickly transferred to a vessel of negligible thermal capacity containing 250 grams of water at 25 degrees Celsius. So copper is at a higher temperature. Definitely it's going to lose heat to 25 degrees water. So copper is definitely losing heat. Water is gaining heat, right? Calculate mass of water that will boil away. So we already know what's losing heat, we already know what's gaining heat. So what's losing heat? Copper. Copper is losing heat. So copper, and then what's gaining heat? The water. The reason for this is so that you don't get confused. You just organize your work. So now we're going to write that all the parameters. So for copper, the mass 300 gram, the temperature 950, specific heat capacity of copper is 4 times 10 to the power 2. So 950 degrees Celsius was the temperature of copper, and then 4 times 10 to the power, or was it 4.2? 4 point, no, here, 4 times 10 to the power 2, okay, 4 times 10 to the power 2, and then 300 gram. So mass equals to 300 gram. Temperature, nice, 350 gram. Specific heat capacity is 4 times 10 to the power 2. Then for water, water is 200 gram. And then temperature is what? I recall 25 degrees Celsius. What about specific capacity of water? Specific capacity of water is 4.2 times 10 to the power 3, as given in the question. Is that right? Then they also give us the specific latent heat of vaporization of steam as 2.26 times 10 to the power 6. So latent heat 2.26 times 10 raised to the power 6. What again? Is that all? Specific latent heat of copper, specific heat capacity of water, okay, everything. 25, 250 gram of water, not 200. So the final steady temperature is 100 degrees Celsius. The final steady temperature is 100 degrees Celsius. So at equilibrium, we are going to be what? At 100 degrees Celsius. That's why I put at the center of the line, right? And don't forget, this was 250. So heat gained is equals to total heat lost. Total heat gained is what? Total heat gain is, we have latent heat, Q equals ml. We also have normal from specific heat capacity, mc, change in temperature. So we're going to add them together. So ml plus mc change in temperature times change in temperature is equal to total heat gained. Total heat lost, sorry, from copper. So from copper, we're also going to have mc times change in temperature only. Copper does not have latent heat in this case. Although it's possible because it's a solid, so it will change state. If copper were to change state, then yes, but then it will have to be what? It will have to be gaining heat. So total heat gained is equal to total heat lost. That's the drill. So this is for copper, this is for water. Mass of water was what? 250 gram. What's the unit they give us again? So kg, I can see kg here. If everything was given in kg, so I have to convert to kg. So we cannot use gram when there is kg in our specific heat. So for 250 gram, convert to kg, you divide by what? 1000. So 0.25. This will be what? 0.3. So 0.25. I can actually factor out m from this and just so I can factor out m. It will be L plus C change in temperature is equals to MC change in temperature. Alright, so M is what? 0.25. Remember, on the left side we have water, on the right side we have copper. So latent heat is what? 2.26 times 10 to the power 6 plus what? C for water, 4.2 times 10 to the power 3 times what? I have to put this in brackets, so times change the temperature. So final steady temperature is 100 degrees. So this is the initial temperature. We are going to have to use 100 degrees as our final steady temperature, right? 100 minus 25. That's what I'm saying, like theta final minus theta cold. So 100 minus 25, that's going to give us 75. So I'm just going to say times 75. Close our brackets is equals to m for copper is what? 0.3 times specific heat capacity is 4 times 10 to the power 2 times change in temperature from a whole 950 degrees Celsius to 100 degrees. How much heat energy did this water even take? Wow, that's a lot. What were we looking for again? I completely missed out what we were looking for. So calculate what exactly? Mass of water that will boil away. Oh wow, that's lovely. 250 grams of water at 25 degrees. If the final steady temperature of the mixture is 100 degrees. Oh. Mass of water that will boil away is the mass from the latent heat. So guys, once again, never lose track of what you're asked to calculate for. So the mass of water that will boil away is that from the latent heat, which is this one. It's responsible for changing state, right? So that's the mass we don't know about now. That was actually unknown. So we can just use m there times L 2.26 times 10 to the power 6 plus what? Mass of water which gained heat, which is 250 gram. So kilogram is 0.25 times what? Specific heat capacity 4.2 times 10 to the power 3 times what? Change in temperature. Remember, change in temperature was what? 75. Is equals to what? M. We had our M as what? 0.3 times specific heat capacity 10 to the power 2 times change in temperature. 950 to 100. 950 minus 100 is what? So here we have theta hot minus theta final, because the final steady temperature will always be less than the hotter body or the hotter liquid or the hotter object. So 950 minus 100 is equals to 850. So times 850. So now we just have to simplify. 0.25 times 4.2, or we can just cancel that from both sides. No, that's not going to work. We can't cancel out here because there's a plus sign. Unless we have to what? Collect like terms and then simplify, but let's just multiply 0.25 times 4.2 times 10 raised to power 3. Oh, there's no 10 raised to power 3 in JAMB Calculator. So how do you go about that? Well, 10 raised to power 3 is the same as 1000. 10 times 10 times 10. You can do that. We can do that, right? So times 75. So we have 78,750 from this is equals to, so multiply this out to have 0.3 times 4 times 10 raised to power 2 times 850. So here we have 102,000. So plus m whatever 2.26 times 10 raised to the power 6 m. Now what we have to do is just what? Move this to the other side and subtract. So we're going to have 2.26 times 10 raised to the power 6 m is equals to 102,000 minus 78,750, and this is going to give us what? 102,000 minus 78,750 . 23,250. So this is going to give us 23,250, and you have to divide both sides by 2.26 times 10 raised to the power 6. So I have to divide this by 2.26 times 10 raised to the power 6. This cancels out, this cancels out. We're left with m. And so m is equals to this. And how do we simplify without a calculator? Don't go and be pressing 10 times 10 times 10 times. Although you can do that, but that's if you have time. Just move this to the top. It becomes 10 raised to the power minus 6. And then you can divide the rest normally. Or you can simplify further. So let's simplify further. So if we say m is equals to 2 times 23,250 times 10 to the power minus 6. 1, 2, 3. I can just leave it here. So 3, subtract 3 from 6, we are left with 10 to the power minus 3. So 23.250 times 10 to the power minus 3 all over 2.26. So this can easily divide on calculator. I don't know why I stopped there, sha. 3.250 divide 2.26. That's going to give us 10.29 times 10 raised to the power minus 3. So we can even bring it back a little again. So we are left with a final answer of 1.029 times 10 raised to the power minus 2. We brought it back once, chapter 1. Like we add 1 rather. So 1 minus 3 is minus 2. And that's how we got this. So our final answer is 1.029 times 10 to the power minus 2. Minus 2 what? Minus 2 gram. and that's the mass of water that's boiled away. I think this mass is reasonable. That's like 0.01 kilogram because we converted our units, remember. 300 gram converted to 0.3 kilogram. 250 gram converted it to 0.25 kilogram. So this our answer is in kilogram. So if we want to get our answer in gram, how do we go about it? Kilogram, kilo means 1000, so 1000 times this. That is, we are multiplying by 10. We are multiplying by 10 raised to power minus 3. Sorry, 10 raised to power 3. That's what it means, 1000. So times 10 raised to power 3, you are going to be left with what? So we have 3 plus minus 2. That is 3 minus 2, which is 1. That is 10. So our final answer is 10.29 gram. So a small quantity of water actually that boiled away. Next question. Waterfall is 1260 meter high. Calculate. Okay, so calculate the difference in temperature of water. From our heat energy formula, we can use energy of fall. So the kinetic energy of the fall of water can be converted to heat energy. So Q is equals to m c change in temperature, right? And then energy is also equals to mgh. So therefore we can equate mgh to mc change in temperature. M cancels out because it's the same mass of water, right? Energy is conserved. So we have GH, height. What were you given our question? What are we asked to calculate? We asked to calculate what? The difference in temperature, which is change in temperature. We're given 1260 as height and 10 as zero to gravity. Specific capacity of water as 4.2 times 10 to the power 3. So that's what we're going to substitute into the formula. So in place of G, we have 10 times height 1260, which is equals to specific capacity of water 4.2 times 10 raised to the power 3, and then what? Change in temperature. Okay, that's what we're calculating. So change in temperature would be equals to 10 times 1260 over 4.2 times 10 raised to the power 3. 10 raised to the power 3 is like saying, so that is 4200. You can just say 1260 over 4200. That will give us our answer. So the answer is 3 degrees Celsius. And that's option B. 18, the ice point on absolute scale. So this is temperature conversion. I want to do something for temperature conversion. On a when we are dealing with temperature conversion, there is something we call upper fixed limit. Let me just write the topic: temperature conversion, or temperature measurement rather. Measurement and conversion. So for temperature measurement, I don't know if this has recording. For temperature measurement, we have different units: Celsius, Kelvin, and Fahrenheit. And there's something we call upper fixed point. That is temperature of pure boiling water at standard atmospheric pressure, which is 760 millimeter of mercury. Then lower fixed point is temperature of pure melting ice at standard temperature. Standard pressure, which is 760 milliliter of mercury, right? The equivalent for the upper fixed point in Celsius measurement or Celsius scale is 100 degrees for pure boiling water, and that for melting ice is 0 degrees on the Celsius scale. But on the Kelvin scale, just add 273, right? 373 Kelvin as the upper fixed point and 273 Kelvin as the lower fixed point. But for Fahrenheit, we have what? 32 degree Fahrenheit for pure melting ice, and then so we have 212 degrees Fahrenheit, which is equivalent to temperature of pure boiling water at standard atmospheric pressure. Okay, so upper fixed point. What's the instrument used to measure upper fixed point? Upper fixed point is measured using a hypsometer. Please don't confuse it with hydrometer. Hydrometer is used to measure relative density. Whenever you hear D, hydro, just know it's density, relative density. Don't confuse it also with hygrometer. So hygrometer is used to measure relative humidity or moisture of content in air. Hydrometer is used to measure relative density. Hypsometer is used to measure upper fixed point of upper fixed point, whatever upper fixed point means. Then lower fixed points. What do we use to measure lower fixed points? Thermometer in glass with ice shavings. There's no specific instrument, or there may be a specific name, but for the scope of this lesson, just know that it's thermometer. A thermometer in a glass, a funnel-shaped glass with ice shavings. So the ice is allowed to melt, and then the reading is taken from the thermometer. That's how you measure lower fixed point. Okay. So, still on temperature measurement and upper fixed point, there's a diagram I need you to know how to draw. So when we talk of upper fixed point and lower fixed point, you should know that I'm referring to the equivalence 100 degrees is the upper fixed point. You can see it at the up. In Fahrenheit scale, it is what? 212 degree Fahrenheit. And then lower fixed point 0 degrees Celsius, but lower fixed point in Fahrenheit scale is what? 32 degrees Fahrenheit. What about in Kelvin? Kelvin scale is what? 373 degree Kelvin. No, it's not degree Kelvin, just Kelvin. Then lower fixed point is what? 273 Kelvin. Now, from these, we're going to derive formulas which we can use to convert between one unit to another unit. So I'm going to wipe this off so we can have some. So we can have some space. Okay. So as I was saying, now let's take a measurement somewhere here and call that measurement, for example, X. Right? We want to compare it to the value on the Fahrenheit scale. Okay, let's use their initials instead. Let's use the initials instead. So instead of x, let's use C here. So a temperature in Celsius compared to a temperature in Fahrenheit, sorry, compared to a temperature in Kelvin. So how do we go about this? Let's first compare Celsius to Fahrenheit. So this is how we do it. Upper minus lower all over middle minus lower. Just remember that statement. Upper minus lower limit all over middle minus lower. It is constant for every temperature measuring, almost every temperature measuring device, even a 40 thermometer. So doing that, we can find the conversion formula for Fahrenheit to Celsius if we compare it to Celsius. So 100 minus 0, that's upper minus lower, over middle minus what? Lower, which is 0, is equals to, for Fahrenheit scale, to have 212 minus what? Lower, which is 32, all over middle, which is minus lower, which is also 32. So we end up at 100 over C is equals to 212 minus 32 is 180. 180 over F minus 32. So cross multiply and simplify. So 100 brackets F minus 32 is equals to 180 C. So here we can actually divide the lowest term. 0 cancels 0. 2 here 9. 2 here 5. So we are left with F minus 32 is equals to 9 all over 5 Celsius. Or another way we can do it is, instead of just cancelling and dividing to lowest term, 100 divided 180 is 1.8. So we can just have F minus 32 is equals to 1.8 Celsius. So this is the conversion formula from Fahrenheit to Celsius. So for example, we are asked to convert 32 degrees. Let's take a known conversion. 32 degrees Fahrenheit, convert it to Celsius. How are you going to go about it? So in place of F, I'm going to write 32. So 32 minus 32 is equals to 1.8. This is 0, right? So 0 Celsius. Let's take another known. 212, for example. Convert 212 degree Fahrenheit to Celsius. So in place of Fahrenheit, I'm going to write 212 minus 32 is equals to what? 1.8 degrees Celsius. 212, that is 180. 180 divided 1.8 is going to give us 100 degree Celsius. That will convert. So these are not the only values you can convert. You can convert any value. You can just say any value random. For example, convert 50 degrees Fahrenheit to Celsius. You apply this formula, you get the answer. So let's relate Celsius scale to Kelvin scale. So relating Celsius scale to Kelvin scale, we can say, remember, upper minus lower all over middle minus lower is equals to upper, the upper fixed point or the upper limit in Fahrenheit scale is what? 373, right? Minus the lower limit. What's the lower limit? 273 over what? Middle, the middle term, that is K. If you look at the diagram, it's K minus lower 273. So simplify 100 over C is equals to what? 273 subtract, you're going to get 100. And then you're going to get K minus 273 So if you cross multiply, you find out that 100 cancels out, and you're going to be left with what? K minus 273 is equals to Celsius. Therefore, if you want to convert Kelvin to Celsius, you just subtract 273. And if you want to convert Celsius to Kelvin, you add 273. That's what makes this formula as simple as that. So we can also apply that same concept when it comes to solving for 40 thermometer or unknown thermometers. Okay, let's answer this question first. The ice point on the absolute scale of temperature is what? The ice point on the absolute scale of temperature is what? So ice point is 0 degrees Celsius. It is either 0 degrees Celsius or what? 273 Kelvin, or what? 32 degree Fahrenheit. So the answer is what? D. 19. A 40 thermometer registers 102.5 degrees Celsius at 100 degrees. If the thermometer has no zero error, what will it register at 55 degrees? When I say it has no zero error, it means it registers 0 at 0 degrees Celsius. So when we're doing upper minus lower over middle minus lower, you know what we're after. So if I'm to even sketch that diagram, at the upper limit, it's the thermometer registers what? 102.5 degrees Celsius, where it was supposed to register what? 100 as compared to a normal working scale, right? And then it has no zero error. They ask what to register at 55 degrees normal temperature. So it has no zero error, meaning that the zero reading corresponds. But what will it register at 55 degrees? That's what they're asking us. So I'm just going to call this X. So upper minus lower, 102.5 minus lower, that is minus 0, is equals to what? Middle minus lower. So X minus 0 is equals to 100 minus lower minus 0 is equals to all over what? 55 minus lower. And then we'll simplify. So 102.5 over X is equals to 100 over 55. X is going to be equals to, just cross multiply. We have, sorry, so just cross multiply. Let me just solve here. Cross multiply, I have 102.5 times 55, and I have 100x is equals to 100x, right? Divide both sides by 100. 100 cancels out, so I left with what? 102.5 times 55 divided by 100. So 102 times 55 will give, in brackets, divide by 100 will give us X is equals to 56.3, let's just leave that 38 degrees Celsius. So at 55 degrees, this thermometer, this 40 thermometer will be reading 56.38 degrees Celsius. Okay, 56.38, approximately 56.4. So this is the correct answer. So D is the correct answer. Then the last question for this video. The ice and steam points of a certain thermometer are 25 cm apart. If the length of mercury thread is 10 cm above the ice mark. So how can I can solve this one under. Okay, I'm just going to draw a diagram. So we're talking about ice and steam points, right? (25 cm apart). So the distance from the ice point to the steam point is 25 cm. if the length of the mercury thread is 10 cm above the ice point mark. So the ice point mark is actually the lower fixed point, right? So 10 cm, so the mercury thread is 10 cm. Let's say this is about 10 cm. 10 cm above the ice point mark. Calculate the temperature recorded by the thermometer in Kelvin. So remember, at upper limit in Kelvin is what? 373. At the lower fixed point is what? 273. So remember the rule, upper minus lower is what? Now in this case it is giving us the distance 25 cm. So that's 25 cm already. Upper minus lower is 25 cm because they're 25 cm apart. Let's say, for example, the top was 75 and the bottom is 50. If they are 25 cm apart, 75 minus 50, that's upper minus lower is 25 cm, right? That's the concept. So 25 cm over what? Middle minus lower. So middle we have 10 cm, right? 10 minus lower. What's the lower point? It's going to be 0. 25, 0. So 25 minus 0 all over 10 minus 0 is equals to, we're looking for the equivalence in the Kelvin scale. So 373 minus 273 all over Kelvin minus 273. So we have 100 over K minus 273 is equals to 25 over 10. That's 2.5 already. 2.5, or we can just cancel out. 25 here is 4. 25 here 1. So we have 1 over 10 equals 4 over K minus. Cross multiply. We have K 273. 10 times 4 is equals to 40, and therefore our final answer is 40 plus 273, which is going to give us 313, if I'm not mistaken. 330 Kelvin. So let's see our options. Yes, we have 313. So this is the correct answer, B. And one more thing before I end the class. Please, there are formulas you need to know. There are other formulas you need to know in temperature conversion. For example, when you are given two different densities of a liquid, a density at a cool temperature and a density at a hot temperature, 2 is related to cubic expansivity as 1 plus what? Cubic expansivity times change in temperature times temperature change. So how do you apply this formula? Let's say you have a substance, a liquid, palm oil, for example, at an initial density. It's thick at first, right? But then when you heat that palm oil, it begins to expand in volume. That's cubic expansivity. But as it expands, the palm oil becomes lighter, which is our second density. So this is the initial density of the palm oil, and this is the second density where it becomes lighter. So what am I even saying? So the initial density where it is thicker or at a cooler temperature, and then so at a cooler temperature, then when you heat it, it becomes hot, but the density now decreases to rho 2. This symbol is called rho. So bracket 1 plus cubic expansivity times the change in temperature through which it was heated. So you know where to apply this formula if you come across a question like that. Just know it.